Hello, Pooja,
Hi, Professor.
can you hear me easily?
Yes, I can hear you
Yeah.
clearly.
Okay, nice. Deepak,
Hello, Professor. Good evening.
good evening. Can you hear me very well?
Yeah.
Who else is there? Pain? Hello, Pain. Ian is here. Yeah, you can come here and say hello. Okay, thank you. Sorry. Yes.
Whoa,
Hey,
Ian
hi.
is still in the school.
Oh, you can see from that side. Let's go.
Oh, yeah.
Yeah. Yeah. Pradeep is here. So, look. So what is the plan? Oh, there's someone chatting, okay.
Oh,
I
yeah.
cannot see the chat, by the way. Talk instead of chat.
So can you just go over homework question 1?
Homework question 1, yeah, sure. Remind me. So homework 5, right? Remind me what the question is. I graded it recently, so it was a circle, right? So it is integral of A, I guess. 1/2 pi.
Yeah, z. Z squared minus x squared.
Correct? Yep. And the question is to evaluate this integral, correct? And the contour is on a unit circle. That's magnitude of z is equal to 1 on the circle. And this is a complex plane. Right. Reasonable? So notice A need not be real, A can be complex. So A could be anywhere in this plane. There are two possibilities. A is inside the circle or A is outside the circle. So let's think of A outside the circle. That means, remember, this is a complex number. This could be anywhere. So that could be A. Right? A is outside the circle. That means magnitude of A is greater than 1. If that's the case, this is a function, analytic function. Exponential is an analytic function, and in the denominator, there are 2 poles. Whenever denominator becomes 0, that's what the poles are. So very simple determination of pole is pole represents when denominator goes to 0. So that's z squared minus a squared is equal to 0. There are 2 solutions. Z is equal to plus a and z is equal to minus a. If this is a, minus of A will be exactly diametrically opposite, so that will be minus A. Minus X minus IY. If A is outside the circle, minus A is also outside the circle, so this has no poles. So if magnitude of A is greater than 1, it has no poles, and if there is no pole, a Cauchy integral tells us that I of A, if there are no poles, this is equal to 0.
Hi, Dr. Sajis.
Yes,
I think the video is not much clear. The writing, like a power, the square, we cannot distinguish that one is square or like a 1 or 0, something like that.
okay,
Could you just check the video?
okay, let's see. We see it good here, right?
Yeah, it looks pretty good. We're good.
Okay.
Everyone has a problem, or this eyes, there's something like a blur.
Is it changing?
It's not much changing. When we follow your voice, we can distinguish. Otherwise, if we see the writing only, then we cannot distinguish what you write there.
Oh, good.
Oh, it is changing, huh? Okay.
Now
Mhm.
that becomes more dim.
Yeah, it's starting to look better.
Yeah, that becomes a little bit clear then. Okay.
Tell me when it is good.
Okay.
Is it getting better or?
Yeah, it's going better now than the last one.
Let's keep going. Tell me when it gets bad.
Okay. Okay.
Non focusing.
Okay, now that's good. It's a little bit blurred now.
So go back. How is it?
I think it's same like at the beginning. Can we zoom little bit?
Yes, you can.
I think if we zoom little bit more, then that should be maybe okay. Not that much. That one is, yeah, now it's very clear, but that one is too much zoom. Can we go a little bit back? One more step back. I think this, oh, that goes whole back.
I think that it is discrete. That the next zoom I have is this.
Oh,
But I can
this
stick
is
to.
very clear, but you cannot also write everything inside there.
Hold on, now we can. Let's see.
Okay, it's awesome now. We can see
Right.
very clear. Yeah.
This is good. So I think that might be. So I'll try to confine to this region.
Okay, that should be very good for us.
Right. I think bottom I have to. Yeah.
Yeah, there's a in the left side. That one is little okay. Now it's okay.
If you go that way on the board, I could probably rotate the camera if you go.
Yeah. Whenever we want, maybe. Yeah. Okay. Is this good?
Yeah, it's now it's perfect.
Okay. Perfect. Okay.
Thank you.
Yeah. Yeah. Like this may not be convenient for the lecture, but I think today we can manage. Okay, that's good to know that writing that small doesn't help. Okay. Okay, good feedback. Okay, so what was I doing? Yeah. So given any complex contour integral, we first look for the poles If there are no poles, there is no contribution, you just immediately say it is zero. So for example, in this case, let me conserve my board space. So that means I of A is equal to 0 if magnitude of A is greater than 1. Is that clear?
Yes.
So the second possibility is that magnitude of A could be less than 1. So that will be the scenario where this is inside. It could be anywhere inside the circle. So let's say this is A, and diametrically opposite will be minus A. So that's minus A. Agreed? So I have now recognized the poles. So I of A would be equal to residue from pole 1. So residue, now there are two poles, residue from the residue due to plus A plus residue due to minus A. Okay. Any questions on that? What is residue due to plus A? First write z square minus A square as, maybe rewrite this a little bit. Or 1 over 2 pi I. Is that readable? Maybe not.
I think we know that one. That's why we can read.
Yeah, you're right.
Yes. Yes, clear.
When you're looking for the pole for plus A, that's this, z equal to plus A. So this one corresponds to z equal to plus A. And this one corresponds to z equal to minus A. So when it is z equal to plus A, you hide this and evaluate the rest. So 2 pi I times whatever is inside, so that's 2 pi I times exponential of Iz other than z equal to plus A pole, so that's z equal to A, no, z equal to plus A. So that's z plus A, evaluate this at z equal to plus A. So that's a pole from the first one, and do the same thing for the second. 2 pi A cancels out, and it is e raised to Iz, this time z minus A. Evaluate it at z equal to minus A. Is that clear? Anyone? So this is straightforward, e raised to IA and 2 times A plus e raised to I minus IA divided by, so that's minus of 2. So that's the same as, this can be recognized as a sine function. So it is I over A times sine of. Is that clear how that process works?
Yes.
And one can also see that since we know how to take a limit, so it seems like it did not, like we have A greater than 0, A less than 0. What if it is really at the origin? So that can be taken as by taking the limit A tends to 0. So we can take the limit A tends to 0 here. And sine A over A, what is the limit sine A over A?
0 over 0.
No,
Oh.
it's 1.
Oh,
Like
is
the
that
limit of sine x over x,
I remember that.
the x, so in the calculus we see it as 1.
Okay.
So this comes out to be I. So that's a simple result you can get. And that is all you need to do. Remember that there's usually one thing that one imagines that whenever A is given, whether it's real or complex, in this context, always complex. Like if it is not mentioned specifically, assume that it's complex.
You said assume that A is complex. is that- Okay.
Yes, whenever not mentioned, if you are doing complex analysis, so things are complex. Christian?
So you always will have the 2 pi I out front and then you do the integral part?
Yes, whatever is in that, so yes, so this is the. So 2 pi, the residue will be 2 pi I times whatever the integral is without the pole, right? Remove the pole from the denominator. This is the first order pole. If it's a second order pole, then you have to take the derivative of the function. Like that was part of your quiz, I think. But since I missed a class on Monday, I'll stick to first order poles.
Is that always the case? You have the first derivative?
First, if it's a second order pole, you take the first derivative. If the third order pole, you take the second derivative, and so.
So the exam will only have first order?
Exam, we will stick to first order. Yeah. Did that help, Fane?
Yeah, that helps a lot.
I have so when we're doing, I remember that. I guess I'm gonna try to figure out how to word this. With this one, we can just use the residue theorem, but depending on, I think in problem 2, you have to choose from the top portion or the bottom portion to evaluate.
Yeah. So when do you do that? How do you do that? Is that a question?
Would you have to prove like the contour part was always to be 0 and then you can evaluate
Correct.
the
But the idea is to build the contour. So shall we do problem 2 here?
yeah, if you
Might help,
I got
yeah.
that.
So let's do problem 2 in a very similar manner. This is problem 2. And I think problem 2 said, again, that is I of A. This time A is real. And it was, remind me, the X, minus infinity.
Yep. And it's e to the IAX
Or
x squared plus 1.
x squared plus 1, which is x plus I times x minus, correct? Yeah. And is there a 2 pi I?
No.
Okay.
No.
Notice the difference that in the previous question, the integral was on a contour. It was on a complex plane. Here it's going from minus infinity to plus infinity, that means x is real. So this is on a real line. So this integral, if I were to show this on a complex plane, so this is complex plane Z. This integral is running from minus infinity to plus infinity, like only on the real line. If this is x, if this is x, and that's y. Z is x plus iy. Is that clear how the integral in this case is very different from the integral earlier? Earlier it was on a contour, it was on a complex plane, it was a closed line integral. This is an open line integral. It starts from somewhere at the very left and ends on the very right here. So it is not a contour at all, or it's not a closed contour at all in this case. If it's not a closed contour, we cannot use Cauchy's. Cauchy's theorem cannot be used. Cauchy's theorem is for a closed contour integral. So since Cauchy's integral is not working here, we would like to build a Cauchy's integral in this case. So this is L going from minus infinity to plus infinity. Close it now. You can either close it on the top or to the bottom. Let me pretend that I'm closing to the top. That's one option I have. And now I can use my Cauchy's integral. So that's a close, but there's no more this integral.
Yeah,
Right? So where are the poles here? Plus I and minus I. So this becomes x equal to I, that's plus I pole, and that's minus I. So the plus I is here, and that's minus I. But again, this is not the the closed contour is not this integral. So I construct that closed integral. This is a new function, which I say is C1 plus C2, where C1 is this part and C2 is this part, and that's a closed integral. This time going through dz because it's a complex integral divided by z plus I and z minus I. Is that clear how I switched from first to the second? I could have done many things, but this is one possibility. Why I chose this is that along part of the closed contour, this exactly is equal to I of A. On C1, this is exactly the integral that's provided. So I can say that G of A is equal to I of A plus C2 Z e raised to I A Z over is that correct?
Yeah.
But we also know that this is a closed integral. So Cauchy's theorem gives us a result. So the result is, so this is also equal to, because using Cauchy's theorem, so here I'm using Cauchy's theorem. Right, using Cauchy's theorem, this is equal to the poles. How many poles are there inside the contour? Only one, right? If I do it from the top, there is only one. So I have to say it is a residue at plus I, which is equal to 2 pi I times evaluate this integral e raised to I a z divided by at z plus I have to hide this part here. So it is z plus I that remains and evaluate it at z equal to I. Correct. That's equal to 2 pi I e raised to I a, z is I, so that's I square divided by 2I, which is equal to, can I write one more? But they can see it, right?
I think they can, yeah,
Or I can just
I can just go.
about this. This is equal to 2I cancels out, so it is pi times e raised to minus a. Is that clear?
Yes.
So. But this is equal to G of A. That was not my goal. our goal is to calculate I of A. The residue only gives G of A, which was my construct. So I have to still evaluate I of A. That requires me to evaluate this. So what is I of A now? I of A is equal to, move this to the right, so I know that that is pi times e raised to minus A minus of integral of C2 is Z e raised to I A Z over Z plus I and Z minus. Okay. So if I can do this integral, I'm good, I will get the answer. So this integral involves the integral on the contour C2. So let's do that. And to do that, so what we can do is substitute Z is equal to, on that circle, I have, let us substitute, let's use Z equal to, origin is also pi. So that circle is represented by R times e raised to I theta, where R tends to infinity. The R is very large, right? This is minus infinity. It goes from, the contour is really large. And theta runs from 0 to 2 pi. So theta is less than 0 and less than pi, actually, not 2 pi. It's on the upper, upper plane. We have to do dz, that's equal to I times R e raised to I theta d theta. Do this, and we learn that this is pi times e raised to minus A minus, there is an R that we have to take limit R tends to infinity, that I write it here. And integral runs from, on theta now, because R is fixed, so it runs from 0 pi, dz is I R e raised to I theta d theta. And so this is e raised to I A, Z is R e raised to I theta, which is also can be written as R cosine theta plus R I R sine theta. Here. And denominator is R times e raised to I theta plus I R times e raised to I theta minus. R is really large, and the limit R tends to infinity. This can be neglected, and minus I can be neglected. So a denominator has two R's. So this is equal to pi and e raised to minus A minus of limit R tends to infinity. There is a 1 over R in the denominator. One of the exponential cancel out. It is 0 to pi. There is an I remaining there, d theta, and one of the exponentials cancels, and we have R e raised to I theta in the denominator. In the when R is really large. What about the exponential here? This is exponential of I A R cosine theta, and this is exponential I times I is minus A times R sine theta. Notice as large as R is large, for a very large R, this will go to 0 or this will go to infinity, so there's a 1 over R. But we still have to worry about the exponential, because the exponential can beat the 1 over R dependence. And let's argue what happens to the exponential. As far as this is positive, this will beat the R or it will die, it will go to infinity. So this is convergent if A times R times sine theta is greater than 0. Let's ask if it is really greater than 0 or not. We are running from theta from 0 to pi. Sine theta is positive for 0 to pi. Right? So that's greater than 0. R is always greater than 0. But A, we don't know what A is, right? A is just real. It was possible that A could have been negative. So as far as A is greater than 0, this will converge and this will go to 0, and that is the answer. So this is the answer. Pi is it? No, cannot be right. That's equal to pi e raised to minus a plus 0, because exponential goes to 0. Only for a if a is greater than 0. Is that clear how I got that argument? Like, if this integral has to go to 0, I need the exponential to really go to 0. Exponential is 0 if a is greater than 0, because sine theta, the way we close the contour, that gives you the reason for it being like that. But then you say, I didn't ask you to do this for a greater than 0. I could have asked you to do this for a less than 0 too. So what happens when a less than 0? If a is less than 0, this goes to infinity. So you cannot say anything about this. So you come back and you say that who asked me to close the integral this way? I could have closed the integral the other way. And I have to restart the whole problem with the integral going in the bottom half plane. Any questions until now? Especially why a is greater than 0, if this why this answer is valid for a greater than 0? Anyone on the online? That's very hard, no responses. Okay. Do you think you will be able to do that for a less than 0, or do you want me to repeat it?
I can do it for a less than 0.
I think we can do.
Repeat that?
I think we can do. I'm okay with that.
Would
But
you like me to do?
I cannot say for others, but for me, I'm okay.
Feel free to ask me to do it. I'm willing to do it. But I'll encourage you to attempt it on your own. But if you ask me now, I will repeat it. I will do that for the other case also.
Okay, let's finish then.
Okay, good. So, shall I erase this part?
Yes,
Or let me,
yes.
okay,
help
let me
you
do the
learn.
following. Instead of erasing, even though it will come at a price, I'll try to superimpose this for the a greater than 0. Not because I'm lazy, so that you have the whole thing in front of you and you see what are the things that are changing. Okay? And is that a red color by any chance? No. Oh, yeah, green. Yeah. Yeah, okay. So I do this for the green. Yeah. So now I'm doing for a less than 0. My guess is that this will happen when this contour works.
Is it different color marker?
Yes, it's a different color bar, but it doesn't show up on the screen. Very good question. Let's bring in another, let's see. Is this different color?
That's so little bit different than this one.
Little bit. Okay.
Yeah. We can figure it out. This one is different color because we are looking this one.
Yeah, I'll try to make it different. Okay. How about this? I write squiggly. Okay, that's different. Oh,
Yeah, this one is perfect. I want to tell you, but I didn't feel good to ask you for the making dot 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 or zigzag something different.
Okay.
That's good.
good. So that's, let's call it C3. Remember that Cauchy integral is valid for counterclockwise. This one is clockwise. Okay? Oh. Thank you. Is this different color?
I think this green one is different than that one. The
Oh. So it's work.
So which one did you say is the best, Pradeep?
that curly one we use the curly. This one is little bit dark, but that one is very close to black.
So this is the best, you thought, right? So this one.
Yeah, that one is little bit bold. That's why we can
Okay,
figure it
good.
out, I guess.
Notice that Cauchy integral is valid for counterclockwise contours. This is clockwise the way I have closed it. What that means is that any integral I write, the residues has to come with negative sign. I will flip the signs. Okay? So this is the integral I'm interested in. This time, I still write my g of z here. What do I change? I'm going to box whatever I change. This one is going to be C1 plus C3. Is that clear what I changed?
Yeah.
Instead of C1 plus C2, I made it C1 plus C3 this time. I again come to G of A. I say C1, that's I of A. And this time, this is C of 3. Correct? What will happen to the residues? First of all, I have, so this whole thing I'm going to change. First of all, I need a minus sign because the contour is in the opposite sign, right? Clockwise contour. And what is the residue? Residue is from minus I. Is that clear what I changed?
Yes.
Good. So now, again, change. So there's a minus sign. Q pi I exponential of I A Z. This time Z minus, so Z equal to minus I. So this is Z minus I evaluated at Z equal to minus. That's the change. The 2i cancels out, pi, this comes out to be, so the answer will be, instead of this will be pi times e raised to plus 3. Is that clear?
Yes.
What else changes? I come back here, now the answer is pi raised to e plus a. So this box here changes to plus. Is it clear? And again, this is now instead of C2, I have to do this for C3. right? But C3 is very similar, except that theta now goes from 2 pi to pi. So what is the change? Theta now starts from 2 pi, like it runs between 2 pi to pi. Like theta goes from pi to 2 pi. Most of the other arguments remain the same, because it's still on a circle. But I have to go from 2 pi to pi. So this integral limits will be, this will be pi, again, that's the same. But this will start from 2 pi. But most importantly, here, when I reach here, sine theta between theta pi and 2 pi is negative. Right? So this one is negative. That means if I want this to be greater than 0, A has to be less than 0. If I want to keep this positive, I want to keep this whole exponential positive. So if I want this to be converging, then A has to be negative. So that means this will be equal to, so this whole answer, I think it's here. This whole answer now will be equal to pi times e raised to plus A plus 0 if A is less than 0. Is that clear how everything remains the same because all the substitution is still on the unit circle? Everyone is so quiet.
I have a question.
Yeah,
I noticed that we're evaluating the sine, but what about the cosine?
what about that?
What about the cosine?
This is if you, okay. Exponential of minus x is like this for x real, right? This is how it looks like. Exponential of plus x is like this. Right?
Yeah.
Exponential of ix is equal to cosine of x plus I times sine of x. This is oscillator.
Oh, okay, so it doesn't go.
It doesn't blow. Like it's within plus or minus 1. Sine of x is plus or minus 1. So this is harmless. It
Okay,
is not going to blow up. We want to kill it. So like kill it means it goes to 0, right? Because then this is 0. So killing happens with this. Whatever this is not going to bother. If this is going to dominate, who cares what this is?
Okay.
So idea is to kill it with this. So we want that to be large, and this doesn't bother.
so, okay,
Does it clarify?
Yeah.
Good question. Because I didn't address what happens to that. The point I'm making is that I would somehow make this 0, then I have my answer. As far as that goes to 0, I'm good. And it goes to 0 when A is positive and sine theta is in the upper half. Okay, because that will dominate.
Okay.
Questions?
I think it's
Again,
good.
you understand why A greater than 0 happens in a certain way. What changes when A is less than 0? And so on. If A is equal to 0, so that is one more condition here, right? In between, when A is equal to 0, But then that whole exponential is not there at all. You can actually redo that whole problem. And then it's only. Then what happens? Then you don't have this exponential at all. This itself kills it immediately. This was sufficient to kill it too. It's just that we were
That
making.
becomes 0 at the last.
0 is what?
For a is equal to 0, even this limit term goes to 0 at the last.
Yes, it will, because this will help it go to 0.
R.
Yes,
Okay.
the whole exponential is not there at all.
Thanks.
Any other questions?
I have one that, but it's not pertaining to this homework. Are we gonna, or analytic functions, the determining if they're analytic or not?
Yeah,
I was kind of reading this, but you can use the Laplacian. If it satisfies the Laplacian, it's analytic. Would that be something
yes,
useful to know on the?
yes.
Okay. So I think it covers not only the Cauchy-Riemann conditions, but also another condition too.
Or
I
if,
understand.
no, if the Cauchy-Riemann conditions are satisfied, you can show that it will satisfy the Laplacian too.
Okay. Alright.
That's one way of saying, so they are not independent. You want me to show that? It's
Oh,
too
it's pretty straightforward. I was just asking a general,
Yeah.
more of like a general question.
good, that is correct.
Yeah. Okay.
And on the course webpage, I have put a preview of the exam. So I've asked what question will be from where,
Oh, okay.
right? Which topics will it cover? But it's very simplistic. Homework 1 is first question, homework 2 is second, homework 3. And I'll base it based on the homework itself. But it won't be the whole problem. I'll make a small problem from the and change it sufficiently that you should have attempted the homework honestly to be able to have attempted the homework. Or if you felt the homework to be comfortably clear, then exam should be fine.
Okay. Cool.
Like they're significantly shorter. The exam questions are short.
Hope so.
Yes. If you know, yeah, of course, it all depends on if you know what is going.
Sure.
Not like some of the question are 3-page, 5-page long. That's that much long question, yeah.
5-page long.
Some of them they are very
Yeah.
long.
Questions, no. I think when I make the exams for the classroom, then it usually doesn't go beyond 1 page. If there are diagrams, maybe 2 page at the most.
Okay, that's awesome. Okay, I have one more thing to ask.
Yeah.
Among 5 questions, you told you will give 1 question from home. Can we do like a do 4 question at the class and then 1 question take back home and then next day we can submit that?
This time, because the Monday class was cancelled,
Mhm.
I decided that all the 5 questions will be from the exam or in the class.
Oh,
So. Yeah, let's keep it like that. So Pradeep, you are suggesting that one of the questions you want to take home?
because we discussed about that at class, that's why we didn't have a last class. I feel like we can do that one. That's why I just
Okay, that's a reasonable bargain. So I will but I will decide which problem to take home. Is that okay? Or you guys want to decide one question to take home?
I think that should be okay. Whatever.
I like that one. Which one, the last one, as you guys want to decide?
Oh, yeah, if I need to take it. Does that imply you would make a harder one?
No. I'm giving, I was suggesting that Each one of you will have the option to take one question only.
Oh, okay.
But that will be very hard for me to grade. Because each one of you might pick an independent question to take home.
Mm.
So. Yeah, is it okay if I just make it simple for me? All 5 questions in the class, okay? Pradeep, is that okay?
We have to say,
No,
okay.
feel free to say no.
Yeah, we already decide one question from home. That's
Okay,
why.
you want it home, okay. So the 5th question will be take home, okay?
Sorry, I didn't get the point.
The 5th question will be take home.
Okay,
Is that what you wanted or?
that's okay.
Yeah.
Because we solve all the most of the homework 5. If you now we solve the 2 question from the homework 5, then definitely we can do this 2 question very much comfortably.
Oh, no. Oh, you're saying because the 5th question is on
Contour.
contour, no. Okay, let me decide. I haven't decided which question will be take home.
Okay.
On Friday, I will decide which one will be take home. Probably not problem 5. Problem 5, I would like it to be in class because we discussed sufficiently.
Yeah, that's why I'm
And
definitely.
I have a question in mind and I expect it to be easier for you guys. Okay?
Okay. Then okay, I cannot make more more question over that.
Yeah. No, feel free to suggest.
When we take the classical mechanics class like the last year, so you did like who like did which problem wrong, they can write the right answer again from the home. So we did that way in classical mechanics.
Oh,
So
yes, good question, Pooja. No, I won't be doing that this time.
okay.
Okay. Again, I might try that in the second exam. First exam, I don't want to do all.
Okay.
I want to see how serious everyone is. And if everything goes well in the first exam, second exam, I will give enough options.
Okay.
And so I
Yeah.
want to be able to use this to assess. That's my point.
Okay.
We are very serious. Maybe the problem is in
No, I was not satisfied with the homeworks.
Okay.
Okay. I'm sorry to say that, but I was not satisfied with the homeworks. Like or maybe my point is I couldn't assess from the homework whether you understood or not. Is that clear what I mean?
Yeah, we got it.
Yeah.
Thank you.
So I need to use the exam to assess.
Okay. Let's see.
Anything else you can think of?
Okay. I think we are okay now. We can take any of the you will decide any of the one question that day.
Yes, probably problem 4, I think.
Okay, let's do problem 4. That should be best. That one is more lenient for us, I know.
So now you want to do analytic function right now? Is that what you
Yeah.
suggested?
Question number 4 will be take home, yeah?
No, I haven't decided that yet. That's probably I said.
Okay, no problem.
Let me not do that. I haven't finalized the question. It's there in my mind, but I haven't typed it out yet.
Okay.
Okay.
Okay, thank you for the clarification, everything.
Yeah.
Will you be available tomorrow, just in case?
Yes.
Okay.
I teach and then there is potpourri, so it's very less time I'm usually there
Oh,
on
yeah.
Thursday.
I forgot. Okay.
Is that good? So shall we start?
Can you upload today's video on YouTube, please?
Yes, I will do that within less than half an hour. Give me half an hour.
Thank you so much.
And like today, like before the lecture, Pradeep was very critical about it is not clear. Be critical, only then I know. I don't use this video. So give me feedback of how to improve the quality. Okay,
Okay, thank
and
you.
we can work on it. And be critical about it. Like Pradeep, you were very good today. That no, it's not clear. So then I will work on it. So if you guys tell me, then I do it. Otherwise, I just set it up and work. In this manner, classroom might be difficult because it's a very small space,
Yeah.
but we can find ways. We'll find solutions, but be critical. Okay? Like together we can make it like function. Okay, so I stop the recording on the phone first. And there is Zoom also at the start. The recording.